Hello, my name is Vikram Gupta. I'm the head of product management here at Cloudian. Today we're going to take you and give you an overview of what HyperStore technology looks like. So for that, I have Balaji with me, who has been with Cloudian from day one and has a lot of in-depth knowledge about how the system works. So Balaji, let's take a journey of how the system operates, and we'll take some examples, and maybe we'll give our viewers a flavor of how the HyperStore technology works.
Okay, sure.
So let's start with that.
All right. So I'm going to start off by drawing the what we call as a HyperStore stack. So just give you an overview of what all the components that are in the system. So the top layer we have the S3 server. We also have our admin server. And we also use Cassandra. Redis. And at the very bottom we have what we call as a HyperStore data layer. And this is a layer that interacts with the disks. So I'm going to call it D1 all the way up to like n disks in the system. So this is a very high-level overview of architecture of our system. So at the top layer, we have the S3 server. This is our protocol handler. So this handles the S3 protocol. All the client requests that for S3 come to the S3 server, it handles the protocol. It does all the checking that it needs to do, and then sends up the and does all the processing of the request. The admin server is predominantly used for provisioning users, adding, creating groups, creating tenants, setting users access keys, secret keys, billing APIs, and all sorts of APIs to manage the system. That is provided by the administration server. And we also use Cassandra for storing the object's metadata. So all the object metadata resides in Cassandra. We use Redis for storing counters. We use Redis for concurrency control. We also store some amount of metadata in Redis. And at the bottommost layer, we have what we call as a HyperStore data layer, and this is a layer that interacts with all the disks on the system. So all the reads and writes of the system of the data actually are handled by this, and this is smart enough to figure out how to map objects to different disks in the system. S3 server predominantly interacts with the data layer to read and write objects. So this is like a very high-level overview of all the components that fit into one of our nodes. And to scale out, you have to just install multiple of these nodes, and then to scale out, you just have to install multiple of these nodes in the system.
Great. So give us a quick overview of how that a user would use an object storage system. I know that this is not similar to a file system or a NAS where you have files and directories. Give a flavor of what are the common things that people have to use when they're looking at an object storage system.
So one very common use case is if you want to store your photos. So that will be a pretty good system. That will be a pretty good system to use your object store instead of storing it on flat file, instead of storing it on flights. So photo storage is one good example, one good use case for object store. So I'm going to walk you through an example of how an object that comes into the system is stored in our system.
Correct. So we have a concept of a bucket and objects. And
Correct.
Buckets are analogous to what a folder would look like, and objects are similar to the files. But I think the beauty is we don't have to maintain a namespace like the file systems, and hence we can scale to a very large degree.
That's correct, yes. So when a put request comes in, when a request to store an object comes into the system, we have the client over here. So it comes into the system. It sends an S3 protocol, which is REST over HTTP, to our S3 server. So the request comes into the S3 server. The first thing the S3 server does is it validates the request. It checks to make sure that the bucket is valid. It checks to make sure that the user is valid. User is authorized. And then once it validates the system, validates the request, it then tries to it looks at what type of storage policy is associated with that bucket. So a bucket can be associated with either a replication storage policy or an erasure coded storage policy. So then it determines how the user wants the objects to be stored in this bucket. And then if it's a replicated storage policy, so assuming your replication factor is 3, it gets 3 endpoints, 3 nodes in the system to store the object. So I'm going to call it node 1, node 2, node 3. So on a replicated system, the S3 server will, after it validates the user, it will get 3 endpoints, 3 nodes to store the objects on the system, and then it will write simultaneously to all the 3 nodes. And we have something called the concept of a consistency level. So depending on what you set, so if you just want to acknowledge a write after 2 of the replicas have responded, then you can set it such, and as soon as 2 of the replicas have successfully responded with a write, we send an ACK back to the client saying we have added the object to your system. Go ahead.
Mm-hmm. So are you referring to the quorum consistency level that we have in our system?
That's correct. Yes, the quorum consistency level in the case of a replication factor of 3, a quorum consistency level would be 3 plus 1 by 2, which should be 2 nodes. So if 2 nodes have successfully committed the data and send a response back, even if third node is slower to commit the data, you would have sent an acknowledgement back to the client saying we have committed your data.
So what is the benefit of that? So why would somebody use eventual consistency versus strict consistency level?
So in this case, if this node is slower, then your request is not blocked, so that your client, you are able to commit your data faster and respond back to the client right away, instead of waiting for one of the slow nodes to eventually catch up. So if this node is really, if something is wrong with this node, if it's slow, then you are not waiting for this node also to respond back. So if you wait for all the responses back, then your response back to the client becomes slower.
Correct. So I get a perfect balance of consistency where I am maintaining my protection level,
correct,
but I'm also not waiting for a slow nodes in the system.
Correct. Exactly.
Right. Okay. So what happens when you have erasure coding, because we support both erasure coding and replication?
Correct. So in the case of erasure coding, you will have to pick your. We have something called as when you replicate the data, what the client sends is stored as it is in the system. So we don't do anything with the data. We don't modify the data. We don't do anything with the data. Whatever the client sends is what we actually store in the system. In the case of erasure coding, we don't store the data as it is. So erasure coding borrows a lot of concepts from RAID. So we split the data into what we call as the K and M fragments. So the K is, these are the data fragments, and this is what we call as the parity fragments. So the idea here is, to reconstruct the object back, you need at most K fragments of the data to get the object back. So when you can tolerate at most M failures. So if M nodes go down, you'll still be able to get your data back.
Okay.
So that is the idea in erasure coded system. So for the flow for the erasure coded system is also pretty much the same. So you get the request to the S3 layer. So as the S3 server then, based on the bucket, would determine if it determines that it needs to be stored as erasure coded data, then it will get this many endpoints. So it will get the K plus M endpoints that are responsible for the data, and then it'll send the request off to so this is erasure coded endpoint 1 to endpoint 1. So the S3 server gets the endpoints, then runs through its algorithm to break the data into different fragments, and then writes it to all these endpoints. And just like similar to the replication scheme, we also support consistency levels on the erasure coded scheme. So if you set consistency level of quorum for erasure coding, then as soon as we have written K fragments to the disk, K nodes have responded with successful commits, we send an acknowledgement back to the client saying we have committed the data.
Perfect.
So that's a flow for erasure coding.
Great. So let us walk through now the get operation, where once you have stored all this data, how does a get operation get successfully done?
Okay. So in the case of a get, same client sends a S3 request, rest over HTTP, down to all the way to our S3 server.
Okay.
So as usual, the S3 server will check to make sure the bucket is valid, the user is authorized, it does all the checks, and then it goes and gets a metadata of the object from Cassandra.
Okay.
So then it makes a call to Cassandra over here to get the metadata of the object. So it gets metadata, gets metadata of the object from the Cassandra. Then, so the S3 server will know, based on the bucket name, it will know if the data was stored as an erasure coded data or as a replicated data.
Okay.
So let's walk through the replicated scheme first. So assuming the data was stored replicas and with an RF equals 3, So then the S3 server will figure out it knows which 3 endpoints previously stored the data. And then, so you have, so it knows which 3 of the endpoints previously stored the data, and it also is smart enough to know that which of these current endpoints are currently the fastest with the least amount of response time. So it will directly send a GET request for that object to that endpoint. Assuming in this case N1 is your fastest node responding, it will send a GET request of the object, GET request for the object to the first the one with the fastest response time. So once it gets a replica out of once it gets the data back from the HyperStore data layer, then it just streams the data back to the client.
Okay.
So that's the flow for the replicated.
Okay.
For erasure coded, it's a little more different since we need more than one node to respond. So for erasure coded scheme, so we have, let's assume, so erasure code, you need to have at least k fragments coming back. So you have EC node 1 all the way to EC node M. In this case, GET request is, in this case, we first send a request off to all these nodes, all the nodes. We send requests off to k nodes to get the k, we send requests to fetch k fragments to k of the nodes. So if any one of the nodes are non-responsive, then we'll send a request off to another node. So we try to see if we can get as k, we try to send requests to nodes so that we can get k fragments of data back. Once we get the k fragments back, we put it together, we reconstruct it, we do the reverse encoding of we do the decoding, we put it together, and then send the response back to the client. So that's a flow for EC GET.
So I have a question around, so if we are using eventual consistency, and if the data was written in 2 places and the third place was still not caught up, and when a read comes, how do you make sure that you always are giving consistent to the latest data?
Okay. So when a read comes, so when a read comes in, we put a timestamp in all our objects. So all our objects internally store a timestamp. So when a read comes for an object, we go get the metadata for that object name. So we go get the metadata for the object. So the timestamp, the last timestamp that the object was written is with the timestamp, is inside the metadata. So we get the timestamp, we get the metadata from Cassandra, then we know what timestamp was used to write the object. Then we go to check to see all these nodes to see if they have that object with the latest timestamp. So whichever node says that it has the object with that timestamp, we get the data from that node and send it back to the system.
Okay, great. So this works very well, I think, like as our viewers are seeing, in a one data center scenario.
Correct.
So give us a flavor of, because one of the key benefits of our product is that it can be deployed across data centers, across regions, or across geographies.
Right.
So tell us how our product helps and identifies and storing the data in a geo-distributed manner.
So for a geo-distributed, so there's a different color for that. So let's assume we have 6 nodes in the system. So 1, 2, okay, so let's assume we have 6 nodes in the system. So these 6 nodes are interconnected to each other. So you could have a situation where you can configure the system so that these 3 nodes belong to DC1, data center 1, and these 3 nodes belong to data center 2. So when you first install a system, you have to create something called a storage policy, a protection policy, and then associate buckets with that protection policy. So you can create protection policies that span just one data center, or you can create protection policies that span across data centers. So if you create a protection policy that spans across data center, let's assume your protection policy says you want 2 copies in DC1 and 1 copy in DC2. So then when you write an object, this is for a replicated scenario, when you write an object, we'll place 2 copies over here and 1 copy in any of the nodes over here. So, and when you read the object back, we are smart enough to figure out, so if your read request comes from read request comes to DC2, our system is smart enough to figure out that DC2 already has a local copy and your read is served from the local data center. Similarly, read comes to DC1, we know we have a local copy, and the data is served from the local data center.
Okay. And so give us a flavor of how the write would work, because now you have to make sure that the quorum is met. So, so if the writes came on either of the places, how does the write work?
So for writes, you again said, let's assume the write comes over here. So we'll write to the local data local node over here, and we'll also send the write request across the WAN to the nodes on the other DC. And then so depending on consistency level, if you say everybody, at least 2 out of 3 must meet for a replication, if you're 2 out of 3, then this would have, as soon as this meets and one of the nodes over here says they successfully committed the data, we will send a response back to this client saying the data has been committed. So it depends on how you want to commit. So you can also say, instead of making sure that both DCs commit, you can say do a local return an ACK as soon as your local is written. So as soon as in that case, as soon as data is written on DC2, you would return an ACK back to the client saying data has been committed to the disk.
Great. So let's also talk about a feature that we have, which we call as replication over erasure coding,
Correct.
which actually gave additional benefits to the customers. So in the replication case, obviously it makes sense. You can define, this could be a classic case of an active-passive data center. If you want active-active, then you can have more copies distributed.
Mm-hmm.
And I think some of our global enterprise customers, they even deploy it as 5, 6, 7, 8 data centers.
That's
and then
correct.
make the data spread.
Right.
So give us a flavor of how when you have replication over erasure coding works, and what are the benefits of that?
Okay, so we'll use the same. So I'm going to use a simple example, and I'm going to assume we have a 6-node cluster, and we want to we want to erasure code the data with data and parity as 2 and 1. So I'm going to say K and M. Data and parity is going to be 2 and 1. In this case, what we do is we write. So we split the data into three parts, 3 fragments. So data is split into 3 fragments, and each of these DC receives one fragment. So let's call it fragment 1, fragment 2, fragment 3. And when we replicate the data, when we replicate the EC data, so then this node could get fragment 1, fragment 2, and fragment 3. So both the data centers have exact identical copies of the erasure coded data. So the advantage of this scheme is if this DC goes down, you still have your entire erasure coded data in this data center.
Correct. Now, tell us also a little bit about the WAN optimization, because since I have replication of erasure coding, do I still have to repair by going over the WAN, or can I repair it locally?
So for repair, you can still repair your data locally. So if your data is, if your data, let's say one of your nodes in this DC goes down and you have to add a new node, and then when this node comes back up, you can just say repair, and repair would just fetch data from the local nodes and reconstruct the entire data and reconstruct the data and write it back as this fragment back, missing fragment back to this node.
Correct. Okay. Now, so let's switch gears and let's talk about like the failure scenarios, because we got to understand how the data gets put and written, and we also got to know how it's spread across different data centers. So let's talk about how we handle errors. So like you can take an example of disk failures, maybe node failures and things like that. So give us a flavor of how do you repair the data, and how does the system become more and more durable? Because obviously when you store petabytes of data, then you want to make sure that data is durable.
So the very basic thing what our system does is something called as a read repair. As the name suggests, we repair the data when you read. So if the data when you read, we know how many fragments are there, the data are available. If for replication, we know how many copies are there. For EC, we know how many fragments are currently available. And what we do is something called as a read repair. As soon as we return a response back to the client, we go and check if all nodes that should have the data have the data. So if they don't have the data, then we go ahead and populate the nodes with nodes that are missing the data with the data. So as an example, let's say for a replication we have N1, N2, and node 3, and this node was down when data was written. You still met quorum, and you were able to write to N1 and N2. And now at a later point, this node is back up now, and the client sends the read request to the S3 server. So it comes to S3 server. S3 server knows that this node has data, so it reads the data from N1, responds back to the client. Then in the background, it checks to see if all the other replicas that should have the data have it. So in this case, N3 will say, oh, I don't have the data. So then S3 is smart enough to figure out that it's smart enough to push the data out to N3 automatically on a read, and then all your replicas are consistent. Okay. So this happens on an erasure coded flow too. So in the erasure coded flow, it would be the same scenario. So in erasure coded flow, instead of 3, you'll have EC1 all the way to EC k plus m. So after we read k fragments back, so once we have read k fragments back and responded back to the client, we go in the background and check if all the other nodes have the necessary fragments, and if they don't have the fragments, we go ahead and read the entire data, reconstruct it, and distribute the missing fragments to the nodes. So that's a very basic repair that happens on every read path. Okay. It's called a read repair. So that's one way to make sure the data is consistent. Now moving on to the disk level. So all the disk management is done by our HyperStore data layer. So you have disk 1 all the way up to disk n in your system. So the way HyperStore works, it stores, it has a mapping wherein wherein objects are distributed across the disk. So let's say one of your disks is down. Let's say disk 3 is down. Disk 3 goes down. Disk 3 goes down, and there are some objects that map to this disk. So when this goes down, HyperStore will automatically detect this. The data layer will automatically detect this disk is down, and then it will automatically map all the tokens, all the data that needs to be going to disk 3 to other disks in the system, other available disks in the system. So data is the data coming in, all the writes coming in, will instead of using disk 3, which is down, will automatically get assigned to other disks in the system. So after this is done, if you're going to replace disk 3 back in the system, it's fine. If you don't want to replace disk 3, take it out, that's fine too. All you have to do is we have a repair command that'll go and balance out. That'll go and pull all the data that belonged to disk 3 before it went down and redistribute it to all other disks in the system. So that's one failure scenario. That's one failure scenario that we handle.
Okay. So let's switch gears, and I know that HyperStore is a very has been built as a multi-tenant system from ground zero. So some of our viewers might have heard that we have a QoS capability. Just give her a high-level sense of how does it protect when you have multiple tenants from a noisy neighbor problem where one user is not able to consume all the resources, and you can create some boundaries in the system. So okay. My understanding is you use Redis and Cassandra and all that in conjunction to do it. It's just a very high level for a flow. So when a request comes in, how do you make sure you don't have a client that is basically consuming all the system resources?
Right. So when you set up the system, you can write a lot of QoS rules. Rating QoS rules for a user. You can write QoS rule for a group. You can or you can write QoS level for the overall system as a whole. Okay. So what happens is when the request comes in, we are able to.
So I think the step one would be to define certain rules. I mean, so in our system, we have different knobs by which customers can define different rules in which, in terms of the store number of bytes it can use or number of bytes they can transfer and things like that, right?
Correct.
So how do you make sure that the rules that have been given are enforced?
Okay, so like I mentioned before, we use Redis to store a lot of our counter information, and for every request after we so before we handle any post, we store Redis use Redis to store a lot of counter information, and some of the QoS fields that you can set are storage bytes, you can restrict based on request rate, so these are some of the examples on how you can restrict a user from spamming your system, from overloading your system. So we have counters stored in Redis. So we have all the counters are in Redis database. So when a request comes in, if it exceeds any of the count, if the user's group has been, if the user or the group has been allocated any of the QoS restrictions, we check to see if the request falls into any of our restrictions. And if they fall into any of the restriction, then we reject the request right away. So Redis will the S3 server will check with Redis to see if the request can be rejected, if the request can be allowed or rejected, and if the request exceeds certain rate, will reject the request and send an error back to the client saying you cannot do whatever operation, whatever you're planning to do.
And I'll assume, so my understanding is that the S3 server can be running in any number of nodes,
Correct.
and you can actually receive this request from anywhere. So,
Correct.
Do you have to check the Redis every time the request comes in, obviously, to make sure you're meeting the requirements?
Correct. Yes. So that's how we scale. So when our Redis actually is a master slave architecture. So every node in the system. So let's say you have this is your HyperStore node 1, and you have all the way to HyperStore node n. So one of these nodes will be running the master, and all these nodes will be running the slave. So then to check if the system exceeds the limit, we go and just check the slave. So that data is local on the node. So the data is readily available. Then once we are done with the request, so if the request passes, if the request can be passed, then we update the counters. That request goes to master, and this is pretty fast. So it gets pushed out, all the update, the counters gets pushed out to the slave. So the subsequent request can, if it exceeds a limit, it will get blocked right away.
So I think we are almost at the end of it. So I also want to highlight one of the another major key innovations that we have is around our having a no controller for all the admin APIs. I think, so give us a little flavor of how we have created a no single point of failure web interface where you can actually go on any of nodes in the system and access the data, so that we don't need any controller separately to be designed for doing control data or management ability APIs.
Right. So our system is pretty stateless, and like we mentioned before, we have leveraged the Cassandra. We have leveraged a lot of
goodness from
Cassandra to be stateless. So like we drew before, the request could come into any of these nodes. So let's say that the request is your object is stored purely in DC2, DC1. Request would come into DC1, and with using Cassandra, using the goodness that is already built in Cassandra, we can figure out that the object was actually objects are which node in DC2 the objects are located, and we can directly go and get the data from that node in DC2.
So the data is always distributed across the whole cluster.
Exactly.
So hence you don't need a separate controller or a machine that is
that is telling us
storing.
Yes.
So I can point to any machine and I can open up my UI and I'll receive the same consistent view.
Exactly.
Okay.
That's correct.
Great.
Yes.
Great. So thank you, Balaji. So I hope we gave you a good overview of how our technology works. I'm sure you have a lot of questions, so please feel free to contact us, and we'd be happy to give you all the details of how technology works. Thank you, and thank you, Balaji, for coming up and giving us all the details.